hope everybody can hear me and see me. So yeah, I think so. I think it's all right. So and then we talk about elliptic cohomology too a little bit. And so today we will continue with discussion of various aspects of K-theory and sort of and point out what is a compare and contrast with what's going to happen in elliptic cohomology. So so let's maybe to set up notation. Let's first to set up a uniform notation. Let denote E be the group of line bundles, so it's pick 0 of some other curve E. So we're so this is for uniformity, where E check is has there's some cases, could be a smooth elliptic curve, smooth elliptic curve, or could be a nodal. So nodal could also have any components, or can have a cusp. And so in which case this E will therefore look correspondingly, E will look, well, E will look as a E, so a smooth elliptic curve. Now, a line bundle on a nodal curve is just it's a line bundle on normalization. Then you have to specify a complex or whatever element of the multiplicative group of the field and how you glue the two things. So this is going to be GM here, and or the additive group of the field. And so then we would like, this is or doesn't have to be over a field, could be. So this is in principle defined in like families over some base. And so we would like to have a functor from pairs of Gx. So in topology, you take this compact topological group. Most of the time, we'll be interested in connected. And so if we have a compact connected topological group, then there's a corresponding reductive group, which will just denote by the same letter. Otherwise, it'll be very confusing if we keep changing this notation. So you should remember that when we talk about like topological spaces with the group action, we have a compact group acts. But if we're talking about algebraic varieties, then the reductive group acts. So because X for us will be both a topological space and algebraic variety. So that's, and so we want a functor, covariant in both what's called L. This is these are kind of superschemes. And super because cohomology is multiplication. The cohomology is usually skew commutative, depending on the degree. And so this is like that. This is sometimes, most of the time, we will be most interested in even cohomology because we will be interested in like classes of algebraic cycles that are an even cohomology. And so we won't notice the fact that there's some supercommutativity going on, but in principle it's there. And so there would be, since this would be, we can also further specify the over. So since every map maps to a point, and this is supposed to be a covariant functor, so this is like the spectrum of cohomology. So this is, so if there was a cohomology, so this is like the spectrum of cohomology. So K-theory is a ring, usual cohomology is a ring, but we can take their spectrum. But elliptic cohomology is not the ring. It's really it's a sheaf of rings over some space, and so we just take that spectrum over. And so this would be over elliptic cohomology of a point. And so what is that? That is roughly like, so this is, you know, more or less as we discussed yesterday, that would be sort of like, it's like G bundles on this E check. Right? So in particular for and this is, we would like them to be maybe direct sums of stable bundles. So that's this, the fact corresponding to the fact that here we would like to have a compact topological group, and its conjugacy class are all semi-simple. So here this G, here this is compact, and this is now reductive. And then this is we would like this, and these bundles are like direct sums of states. And there's of degree 0. And this picture has some is more complicated, gets more complicated. So this is just to point, so it gets more complicated. If G is not connected. I don't know, you have to discuss what is it, what do we mean by that? So then we will have to, well, anyway, so this is a separate discussion. And so so for us, I'm going to postpone the definition of, well, I think it's better if we first talk about elliptical homology, then we'll try to define it. And so for us, actually, the main point is that we will be able to understand a lot of elliptical homology just by analogy with K-theory, and using the fact that maybe Jacobi sort of take over C, or Tate over maybe P-adix, or maybe QP, let me say QP, whatever QP. Will tell us that we can write E as a quotient of the multiplicative group by translation by some element of norm less than 1. And so in that sense, we would be able to make to understand a lot of construction elliptic homology just by doing the corresponding construction in K-theory and kind of make it a Q-periodic, wrapping it around. So this may be a way to say that's one. So this is, since I haven't defined what elliptic homology is, but you can imagine this is if you have a construction in K-theory and you can kind of wrap it around Q-periodically, that would be construction elliptic homology for not every curve is of this form, but whenever over C, every curve is this form. So that's check that it's going on here. So okay, cool. And also another kind of useful thing to think about. So another picture to keep in mind is that the elliptic homology of X is, with these pictures, we remember when we had the picture of a loop and then a torus, so not yesterday, last week, and then from many other perspectives, this is like the K-series of loops in X. So this would be particularly important for us, because remember when we were a long time ago, we were talking about interfaces on the remote surface, and that's where the loop lives. And when we do some computation with indices of differential operators, that's they're really computing here. So this is really kind of, so sort of, this is this perspective of what is two fundamental to the quantum field theory that we had discussed at the beginning. But well, I think it's so is many kind of important notions in mathematical physics. It's much more it is much easier to define them separately mathematically than to make sense out of heuristics like this. Although this heuristics like this can be justified. I think it's so all right. So now we go back to the discussion, and so we really just discussed, so far we discussed the K-theory of really just one space, right? So we took, like we take the K-theory of, and so now maybe I'll write, so when I write GL, it means, I also mean U. So it means if I write, we wrote something GLV of POV. Right, so this is in algebraic K-theory, that's okay, because so this makes sense in both algebraic and topological K-theory. The result is the same, and so in but I'm just repeating what I said before. But in topological K-theory, you should really think not about this reductive group, but rather it's a maximal compact subgroup. And so we decided that this is you take GLV current K-theory of a point. And this is actually true for, so the way we computed it, so maybe I'll write it like this. We take any group G, doesn't have to be the whole GLV, so we take group G that sits, well, sits inside of GLV. It doesn't have to be the whole group. And this would be, we'll talk about this will be important. So we take the projective space of V. That is the same as KG of a point. And then the adjoint one variable S. And we mod out by relations that maybe I'll write it like this. It's a product of 1 minus EIS equals 0. But these are the Chern roots. Of V. So this means that this relation really means is that the relation is summation over I minus S to the power I, ith exterior power of V equals 0. But then this V will, under the action of G, will split into some reducible representation. And then, for example, if it's a maximal torus, it will just split into eigenvalues. Like, for example, this, you can imagine that this is like splitting of this V restricted to the maximal torus. Okay, so, and so this means that your K-theory of G-current K-theory of projective space, what does it look like? It's you start with the so maybe this is the spec of or I'll write already in the elliptic homology cases. So this would be, so that we don't have to. So we have uniform notation. So there's like a spec. This is my LG of a point. And then I add one more copy of, so this is adding one, this is what? These are the functions. These are functions. On C star, whatever, or G or multiplicative group of a field. And so I add one more copy of E. So this is IE. So that is to say, this is my curve E. And then I have a scheme which is where this has coordinate S. And then my scheme is a lot of kind of looks like that. So it's a union of things where S is equal to VI inverse. Okay. So our first observation is that exact same argument, so just literally exact same argument applies. So literally the same. So we get exactly the same argument. Applies to, you don't have to be V, you don't need V to be a vector space over a point. You can have a bundle over some other space X. So this is a bundle. Like, for example, a crucial point of this computation when we remember when we're computing the current K theory of projective space, we had to think about take the K theory of X, and then there was this map, and this is, so what was we had G cross, so V is a quotient by GL1, so G cross GL1, this is where that variable S lives. And then of X, there's a push forward map, so this is I push forward into the total space G cross GL1 of the total space V, and then this was the map to the quotient. So this would be, I'll just write already the KG of P of V. But now this is now G means some group that acts now on both X, and so G now acts both on this and on the total space. So then so it's an equivariant vector bundle, so on equivariant vector bundle. And so this was surjective. And so this is what this map has the exact same Kazul resolution as we had it for over a point, just literally the same. So this is so the conclusion is the picture. So this is conclusion of this object here. So is you take the current K theory of X, you add one more variable S, and you modify it by the relation that the product of 1 minus S times VI equals 0, where these are the Chern roots. So this means this is a scheme. This looks exactly as before. Maybe let me copy this here and paste it here. Except here I take, instead of a point, I take X. So same. Okay. All right. And so with this we can, says, remember in Igor's lecture already appeared Thom space of a vector bundle, and that's an object which significance of which is, maybe it takes certainly for me personally it took a while to appreciate the significance of Thom spaces. But so what is a Thom space? Thom space is that if I have a vector bundle over X, I draw it like this. So this was X, and this was a vector bundle called E. And then I can either take I can either take the unit ball bundle and collapse the so this is kind of, this is picture. So for some point x, and this is v over x, and so then there's some other point x prime, and there's a v over x prime. And we can either take the maybe unit ball bundle and collapse the spheres all of them to one point, or better, so maybe, so this would be all this would collapse. So maybe another, maybe a better picture is that if I have, if I take my, imagine my vector bundle being a normal bundle to some embedding, but in fact normal bundle to the embedding in the total space of the vector bundle. So sorry, maybe I'll just draw a curved picture so that it can use it later. So this is maybe x, and then there's this vector bundle. So this is v, and then there's kind of the infinity of a vector bundle, which we all declare to be one point. So this is like a, this is the Thom space. I'll just write Thom space of a vector bundle v. And for us, we can take this infinity to be we can take this infinity to be the projective space at infinity. And then if we add this, so maybe we're drawing in red. So this is the projective space at infinity, and this is embedded. This sits inside the total space of, you take the projectivization of v plus a trivial vector bundle over x. So if I take projectivization of v plus a trivial bundle, this will have a big cell which is v itself, and then the projective bundle is infinity. So we can write the Thom space in as you take, like I said, so it's a projectivization over x of v plus a trivial bundle, and then or you can write c. Well, let's see. I'll write root O of x. So sorry, this is maybe not the best notation. Then mod out by p of projectivization of v. It sits at infinity there. So this is like, so this, you should think of Thom space as like a twisted suspension. So this could be, so this is twisted in two different ways. First, the kind of spheres, the spheres, they vary over x in a way that so this twisting happens both in bundle. This twisting both in bundle and the G action. So both the first bundle could be non-trivial, and so if I have a trivial bundle, the trivial G action, that's really the suspension with the induced, so to speak, with the induced action. But I can make the, well, sorry, iterated suspension by some degree. So then, but I can make that to be both the bundle be non-trivial and the action be non-trivial. But and so then what is this? What's this? You know, what's the K-theory of the Thom space? So, well, it's a special case of something we computed. So let's just copy. You know, maybe I still have that thing still here, so I can still paste it. Yeah, it's still here. And so Now, the new thing is that I have a projective space, and it has so I have, see, I had some vector bundle V, but now I also have a trivial piece. So a trivial piece has a trivial Chern class. So it means I also have a piece where S just equals 1, right? So in other words, the K theory or whatever elliptic, so this would be the same in elliptic homology, but let's just write K theory of the Thom space. What's it going to be? These are the functions. These are functions on the whole thing. So this is a union of the green ones and the blue one that vanish. So this is not how I spell vanish. That vanish on just the green part. Right? And so this means my functions, well, they all zero here, and they can be something non-zero here. So, but then means they this means that, but they have to vanish where that blue thing intersects the green. Is that clear? So this is really, this is pretty much the ideal. So what would be the ideal if this were all a good, it was a good kind of intersection, then it would be the ideal of where does this guy intersect. So this is ideal of product of 1 minus VI in K theory of X. And this is all equivalent. So this is equivalent. All of my K theories are all equivalent. Of course, it could be that there could be a trivial bundle among these VIs, and so this would be not so good. This is why this is a proximate sign. The correct statement is that you have where do all these Chern classes live? All these Chern classes live, where do they live? So this is, if I have a vector bundle, means, so we talked about this last time. So if I have a vector bundle, V defines a map from X to point mod. So maybe this is just a Frank R, Frank. R, so point mod GLR or UR. And so then, so this is, therefore, there is a map from elliptic homology of X and whatever covariance there is to elliptic homology of GLR recurrent elliptic homology of a point, which we decided this is the R symmetric power of E. This is where all these VIs live. So this is a point here. Is that point V1 ER. All right. And so what we're pulling back is really, so maybe we call this is like a Chern class. So maybe we call this Chern class. And so then this says that the Thom's, well, kind of maybe I'll write Thom sheaf. Of V, because it's like the case here of the Thom space, but if you're an elliptic homology, it has to be a sheaf of rings over something. That is just the pullback by that of what? Of where one of these guys vanish. So this is well, I will just write down. Well, let me just write down so this is the ideal of what is that? So inside here, there is an embedding. Well, there's a map from the smaller set. There's a divisor. Namely, these are the guys of the form where you have one of them up to permutation, one of them is 0. So this is inside of my R symmetric power, there's a divisor R-1 symmetric power. So this is, and that is, if you think of this as a moduli of GL bundles, that's the theta divisor in this module. So this is theta divisor. Divisor, maybe I'll just d theta. So if you have some moduli of bundles, what's the theta divisor? Theta divisor is where you like, for example, these are those bundles that should mean, suppose your moduli is such that you don't have any sections, but then it could be that in codimension 1 you start having sections. Right? For example, if I have well, this is like Jacobian of a curve. If you're on right degree, you get a section in codimension 1, and so then that means so similarly, if I have some GL bundle over, then it's, for us it's a sum of line bundles. A generic line bundle in elliptic has no degree 0 has no section, but it does have a section if the bundle is trivial. And so this means this is the locus where my rank R bundle, which had no section before, since it has a trivial part, it now has a section. So this is a GL bundle, GL, or as I said, bundles with a section. So this is the ideal that is therefore O of minus this d theta divisor. And so this is so then this is by definition when we set this to be. So if we pull back the theta divisor, we by definition set it to be. We denote it theta of minus e. And since we pull back minus divisor means the functions that vanish. Plus divisor means functions that have a pole. And so this is both a computation and a definition. A computation says we have we pull back a particular line bundle under this Chern class map, and then also we denote it by theta, which is just convenient. So that's and so this is kind of very important point. Maybe I'll point it out. Thom isomorphism is not an isomorphism. In elliptic homology. Okay. So maybe this is the reason to maybe the reason to appreciate the depth of a statement. It's like, a statement is really deep if it's false. If you think, I mean, if you read well, certainly I'm speaking for experience. If you read a generic algebraic topology textbook, maybe you don't feel the dramatism of Thom isomorphism until you realize that in fact it's not something obvious because it's false in more generality. But it's not false. It just says that this object that we want to compute, it's very close. So this is what's the name of the game. Previously we had cohomology was a functor from spaces to cohomology was a functor from spaces to rings, and but now they go to schemes, right? So that's and on a scheme we can have many line bundles. We don't need to have we don't need any other line bundle on elliptic cohomology. Just as good as a line bundle before. So this is you don't need some object to be a section of the structure shift. It could be a section of some other line bundle. And so that's so in elliptic cohomology you have to deal with line bundles. And there you get interesting line bundles on the spectrum of elliptic cohomology, and you have to live with them. And that says this kind of the Tom Schiff is not a trivial line bundle, but it's this line bundle. That's as good as it. Maybe speaking about theta functions. So speaking of theta functions, so maybe apropos. So what is perspective? What's the ordinary theta function? So what is that? What's that? So this is you have S0 of the elliptic curve itself. This is going to be a case for rank 1 case here. So 0 of elliptic curve, that's embedded into elliptic curve S1. This is the this means 0. So this divisor d theta, that's just the divisor, that's just 0, right? The origin. And now the many, I don't know how many braces do I have to put? Maybe I'll put like divisor of 0, just 0. It's just 0 inside of the elliptic curve. And that divisor has one section by Riemann-Roch. So in that section, well, it's just the map has so O of d theta has one section. So this is but just the constant function. So O goes to O of this d theta. So unique, this has one section. So this is a constant section, or maybe tautological section. Which is unique. And it's obviously unique map to multiple. Well, it's just unique in the sense. Unique up to multiple. Unique section of that line bundle. And that is the theta function. Don't recognize the theta function. You should think, so now, well, this may be, okay, if you don't recognize theta function, you should think of this, what's it going to be if I write my elliptic curve as a quotient of the multiplicative group by q to the z. So that's more important for us. So then I'm asking for a function which is has some q. So what does it mean? I have a section of a line bundle on a quotient. Means I have a function which has some transformation law under the shift by q and vanishes at the unique point, namely at the origin of the elliptic curve. So the origin here, so here the origin here is 1. Here that is 1 as the origin, because we take it with this multiplicative group, and here we use additive notation. This is a multiplicative group, and so then the theta function becomes interesting. And then in fact, so this is you get the expression that you like, and then maybe I'll just show it behind. You can see it behind me here. So this is if you mean, you either have seen it a million times and you love it, or you don't love it, but it is what it is. It's the correct, in blue you see the correct transformation law, so that you have unique zero at the origin at x equals 1. Moreover, if you allow yourself a square root of your variable x, then you can normalize, like in red, you can normalize it so that it's an odd thing with respect to, so this is, the divisor itself is centrally symmetric. So if you take your elliptic curve and you take it minus, the zero divisor stays put, but the section changes sign. And well, it depends how to normalize, but you can normalize it so it changes sign, but for that you have to introduce a square root of x. And so, which is expression above. And it's clear from this expression that it's A has a unique zero at 1 in the fundamental domain, and second, that it converges if the norm of Q is less than 1, either real or p-adic. And so that is this construction. This is Jacobi plus state. So this is, so if you in other words, if you want to actually write formulas, then this is what you see. All right, let's go back to the Thom spaces. So but now I said that in elliptic homology, this Thom isomorphism is not really an isomorphism, but it's useful to know that in K theory, of course, in K theory, we do not have that effect, right? This is theta of minus V is isomorphic to O. I'll just write O is just K theory itself. Okay, I'm not going to write O over the spectrum of the K, it's just K theory. So this is Thom isomorphism. So in K theory, the K theory Thom space. So right? because on the multiplicative group of a field, if you want to a divisor, but it's a trivial divisor. So there's no the Picard group of the products multiplicative group of fields trivial. So in K theory we have Thom isomorphism. So this has the K theory equivalent of the Thom space of V is actually isomorphic. Current K theory of X. But this isomorphism is really via multiplication by some element. So this is the multiplication by which we were. This is the isomorphism is really kind of by multiplication. By product 1 minus. That's okay. So what does this so this maybe it's curious to point out, what does this mean? Like, for example, in particular, if I take the Thom space of a trivial bundle, just take a trivial bundle over X. Well, like I said, that's just a suspension. This is going to be what is suspension? I can't really draw the 2 as sigma 2 so well, so maybe I'll draw sigma 1. Sigma 1 of X is that you take so. What's it going to be? So you have your round X called like that, and then we take a bundle of the product with the. So this is going to be, you take disk bundle over X, trivial one, and what we're gonna glue together, we will collapse we'll collapse the boundary. So this is going to be S naught cross X. And then and then if we want to something with a marked point, we will also have to collapse the fiber over marked point. So maybe a different color. So this is the boundary will look like. I wish I picked a simpler shape, but I'll try to. That's the boundary. This is what we collapse, but we also collapse this fiber over special point. So this is my point marked point X naught. Right? And so what we get is just like two cones over X glued together. So we get like one. Sorry. So it's like one cone over X. And then another cone over X. And then there's this marked point which we collapse here, or whatever. Maybe I'll just draw a marked point as what we're collapsing here. So this is something like this you can do in any dimension. And so then so in particular, if this one-dimensional disk was two-dimensional disk, this is like a boundary of a trivial S2 bundle, and that's trivial disk bundle, and that's all right. So and so then it says that for any X, so Thom isomorphism says that the K theory of the twofold suspension of X, that is the same as the K theory of X. Okay. Well, that's just really about periodicity. Maybe I'll explain why it is. Because what's K theory? So if I have actually in general, so if I have a CR, we discussed this, but let's go over that one more time. So the CR bundles over X. Well, how can I think about it? I can think I have this is my X, and I have a bundle V over that of some rank. Well, every bundle I can write as if I pick enough sections, I can write any bundle as a quotient of some trivial bundle of some rank. This would be quotient, and then there's a kernel. And so that is to say that if I write X as a quotient of a trivial bundle, means I have a map from X to the Grassmannian of codimension R subspaces in n-dimensional space. Or if I pick a metric, I can do dimension R subspaces instead of codimension R subspaces. So this is the same. So this is the space of this bundle that is the same as the homotopy classes of maps from X. The square brackets means, you know, we study homotopy classes of maps to the space which is Grassmannian of R-dimensional subspaces, and this will convenient to let, since we don't know how many sections we will need to generate V, it's convenient to let it go to infinity. And so this is the space which is called this is the quotient. This is the classifying space. This is BUR. This is the quotient. You take a matrices of full rank of size R times infinity, and you mod out by UR. Something like that. This is a contractible space, and that's the maybe if I write it like this, then it should be GLR. And if you take this some kind of Hermitian norm, and then if you take the moment to be norm 1, then you mod out by UR. Okay, so this is, so now what are then, so what is then, so this is, and right, sorry, I forgot to say, so this is our bundle. So in K-theory, we study bundles up to stable equivalence. That is up to adding, up to trivial summations. Means you can increase the rank of the bundle, well, if you remember that your original bundle had certain rank. And so then therefore the K-theory of X, that is just the same as the homotopy class of map from X. Now we have to remember the rank, so that would be, this is where the rank lives. And then you cross with BU, which is the same thing. We'll just write BU infinity. And this is this group. This is top. It's not a group, but it's group up to homotopy. With respect to direct sum of the bundles. If I take, right, so this is that makes sense, right? So this, and so this is how this is the additive structure in K-theory is just it's the fact that you can take these two maps, and if you add them in K-theory, then the what's going to happen? The ranks add, and the corresponding you know, like the corresponding data here is going to just like two matrices is going to stack one on top of the other. So that's the group. So now if we want to do the K-theory, not sure what was happening here. Want to do the K-theory of the suspension of X. So then this means well, let's just go back to this picture. So if I have a vector bundle on this, a vector bundle on the suspension, here is just a clutching function here. Right? Because you have bundles of two cones, and so you can trivialize it on each part of a cone, and then as you glue them, you get a transition function. And so that is just, I mean, for every point on X, you have the value of your transition function, and so this means that this is going to be the homotopy classes of maps from X to, well, just U infinity. Right? That's one thing. Well, the other thing is the suspension is a space just like any other space, means that this is a map from S X to the Z cross BU infinity. But the maps from the suspension just kind of obviously. So what does it mean? Suspension is like a collection of loops parameterized by your points in X. And so therefore maps from the suspension is the same as the maps from X to loops. So loops. This is true in general, so loops or whatever. And so this says that this has to be, we'll just write Z cross P. And so this is for any X, the maps here and the maps there are the same, but in fact, so these are just homotopy equivalent to U infinity, this whole loops. And it's a general principle. So if I have like a loops in the classifying space, that's the same as my original group. This is a good exercise to do. But now Bot tells us, so this theorem we just proved tells us that the K-theory of the twofold suspension, that's just again X going to U. And so then this means that this thinks that this object is now, so this is we take, so this object is looped at this, but that is loops in your original thing. So that's, so you have an infinite chain of spaces, each of which is loops in the previous one. So that's in particular, if I take what you want to know, the homotopy groups therefore are periodic. The homotopy groups of this space, in this space, they're periodic and they differ by shift by one. That's so incidentally, okay, so that's the statement about periodicity. Now, what's an elliptic homology? What should be if I take the, so this is in general. So this is, I was my plan to talk about this today, but it seems like we're probably not gonna get it. But in something called stable homotopy category, so you should think of suspension is like shift. It's like the shift by one for complexes. So certainly, if you want a cohomology of suspension, that's one of axioms for cohomology theory, that the cohomology of a suspension is shift by one. And so then, so this means if we want to, so this means you usually defines K, well, because some cohomology theories are kind of, minus, this is the way the shift goes, minus I of X, that is the ordinary K, maybe I'll write it 0, of I-fold suspension of X. And so then if we compute, if you want to know what's O kind of, let's take -2 of elliptic homology of X. Right? So this is we're asking what is going to be the Bott periodicity in elliptic homology. Well, so this should be ordinary elliptic homology of the suspension, twofold suspension of X. Okay, we have Thom isomorphism for this. So what we're going to do, this is going to be, so this is like the pullback of what? Well, we know what it is. It's like of O, just write -0 This means 0 is the divisor. Maybe we'll put divisor class like this. So I can't really couldn't think of some good notation. So this is divisor. So there's a 0 divisor, which is 0, but it's also divisor of a 0, which is a divisor of degree 1. So I find it very confusing to write this notation. All right, so what is that? So this is, so we have, and so what is C? Where C, so this is a trivial, this corresponds to a trivial bundle. A trivial bundle means with C equals 0. So I have, in other words, we have a map, we have an elliptic curve, goes to elliptic curve, and that map is multiplication by 0. So there's like a diagram of a million zeros, and we have to chase that diagram. So this is, so that means it just really takes the whole curve and maps everything to the point 0. Right? And then here we have to, or maybe, sorry, this map is this is a 0 map. And then here we have a line bundle, which is O of minus 0. And we have to pull it back. So this is, okay, so this is a 0 map, it's a constant map. That means when we pull back anything, there's going to be a trivial line bundle, right? Trivial line bundle with maybe, but the fiber will have to, we will have to name that fiber, because the way you should think about that, the elliptic curve is just not one curve, but you have a moduli of elliptic curves, and you should any construction we do, we have to do uniformly for all elliptic curves. And so if we have a, even if it's a line bundle, even if this line bundle is trivial on a particular curve, that still has, it's still over the moduli, it's still a line bundle. And so what is that? So that is, so this is like the fiber. So this means, so this pullback, so to continue this chain of equalities, so maybe I'll trivial bundle over E with fiber, which is what? Which is the fiber, which is equal to the fiber of minus 0 at 0. Okay. So what are they? What are these? These are functions. So what's about? These are functions. This is a line bundle given by functions. These are functions that vanish at 0. Right. So this is, i.e. this is the maximal ideal of that 0. And so this means that we want to compute a fiber of a line bundle, which we have to take this and mod out by m naught times m naught. So that's square, right? This is, you want to know, you want to compute your fiber of your shape at a point, you mod it out by the actual maximal ideal. So this is this quotient, and that's by definition, that's just the cotangent line at the 0 to the curve E. That object is, so this is a line bundle on the moduli people somehow familiar with notation of enumeration geometry, that is this psi1 bundle, right? So you have some kind of moduli of pointed curves, then the cotangent line at the cotangent line at the marked point, that's a line bundle over moduli called psi1. And so that is to say that so maybe so this says that if I want to compute O of minus maybe 2k or whatever, k minus 2 I minus 2 of Lx is the same as OI Lx all times this psi1. So that's the periodicity. That's what kind of both like periodicity in elliptic homology that takes this form. All right. So then the next topic to discuss is since we were still on discussion of Thom spaces, and so what's up? How do we define push forward? So in algebraic key theory, we define push forward as derived as the action on K theory of the corresponding map in just derived categories of coherent sheets. So, but now how would they do the same thing topologically? So push forward. So that's an important topic. So push forward. So this is defined not pullback are defined for any continuous J-equivalent maps. This push forwards are not defined for any maps. They're defined for something called complex oriented. Okay. And the way that it's defined is this is going to kind of copy what we did. Remember when we discussed push forward in algebraic geometry? Of course, you can define push forward just whatever. But it's convenient to factor every push forward into inclusion and projection. And so this is the same. So the map is called complex oriented if I can embed, if I can factor it. So if I can, so I have my space X, and I have my space Y, and then I have a total space of a complex vector bundle over Y. So this is this V over Y, this Y, and this map here P. This is a complex vector bundle. So in algebraic geometry, we took like a projective bundle, but here in topology, we will take a complex vector bundle. And then we would like, so this is a projection part. And then we would like an inclusion such that the normal bundle to the inclusion, so this is the inclusion, such that the normal bundle is also a complex vector bundle. So if I compute the normal bundle to the inclusion, let's call it inclusion I. So maybe I'll write normal bundle inside V over Y to the inclusion of X. This is also complex. And then I have a situation where I drew it here behind me. If you can, hope you can see it. So we have the two-tone isomorphisms, namely, so this maybe I'll write it and then I can point to the picture. So we have I'll write it already in I'll write it already in elliptic homology. So if I take I have a map from how should I say? Maybe I should like this. So if I take the theta bundle of minus that normal bundle, right? Well, this is over X. This is the same as, like this is like O of elliptic of the Thom space of the normal bundle, right? And then we have the elliptic homology of the Thom space of V, and that is isomorphic to by the same token is O over Y of V. And now here we have a map. This map induced by the so there's a collapse map from here. There's a collapse. So from the Thom space of V, I can take everything which is not in the neighborhood of X and collapse it to a point, and I would collapse. So this is the picture. So I take everything. So I took the Thom space of V. Everything which does not fit in the neighborhood of X, then I can collapse to a point together with the boundary of that neighborhood. I'm going to get to the Thom space of the normal bundle. And so this is a continuous map, and therefore by functoriality there's an inverse map on functions, and therefore direct map on the spectrum, but on functions it's like this, right? And so that is to say that for the push forward is really a map from so push forward. Just goes, that's the snap. So this is, you go to the Thom space of the normal bundle to X, going to the Thom space of this bundle V. Okay. But then, so this maybe already noted F. So this is, maybe I'll denote it with some kind of star. But then you can so you can twist both sides. There's kind of a, this is a map of line bundle. And you can twist off both sides by a line bundle. There's a tautological map. We take the Thom space on X, and you take the pullback of V goes to, just because both are pullbacks, so both go to, in both, they both pull back from elliptic homology of They're both pulled back from. Just write things like that. Take elliptical homology G rank V, GL rank V. Point, right? So, and so this, if we twist it by this line bundle, what we're gonna get is it's really goes from the Tom sheaf of minus the normal bundle to the inclusion plus the pullback of the bundle kind of V. This really corresponds to the projection. And this goes to of elliptic homology of Y. This together, this is these two things together are called, this is called minus the normal bundle to the map. So if you want to define a notion of a normal bundle to a map, you can define it if your bundle is if it's a composition of inclusion and projection, and both with inclusion with some normal bundle which is complex, and then projection with along the fibers of a complex projection. And so then this is defined like that. This is normal bundle to a map. It corresponds to the notion in algebraic geometry. So the normal bundle for a map in algebraic geometry is defined using the graph of the map. And if you think of what's happening here, it's exactly what's happening here. So that's the definition. And so maybe a moral from the definition is that now there's in this push forward, the inclusion and projection come with opposite signs. Right? So so maybe I don't know if I emphasize this or not, but when we define these theta bundles, then the theta, so we have used it here. So we have define. So maybe we go all the way back. We go back here. Maybe here. Is that this theta? So this theta with direct sum that is the product of individual thetas. And why is that? Because it just means, so what means direct sum? We have two sets of variables, and we ask in two sets of variables, where is the divisor where at least one entry is 0? Well, I mean it's the union of two divisors. First, we're in the 0 in one half, and then there's a 0 in another half. And so that's this is what this thing is. And so theta is really well defined as a map. so this somehow going back here, theta is really well defined. So we will use this here. So we already have used this here. So that theta is just really a map from K of X to pic of Lx. For every bundle, we get the line bundle. And so what was the moral of this computation? The moral of this computation is that so we used to think of push forward as kind of integration, right? I mean, if you projection, that's like integration, there's an inclusion. And the fact that they come from the opposite sign is that this integration is like 1 over inclusion. And means means like, when we take about inclusion, when we write formulas, they correspond to the product of theta functions of maybe xi where these are the Chern classes. These are the Chern classes. Oh, sorry, Chern class, Chern roots. Of the normal bundle. And when we integrate, then we have to, then in the formula also appears the theta of x size, which these are the same of the tangent. So if you use the writing, say localization formulas, any other kind of formulas in cohomology or current K theory, more or less, all you have to do is you have to take wherever you saw x in ordinary cohomology, you put theta of x in elliptic cohomology. That's more or less all you have to do, and you put the. All right. So then I'm not even at the beginning of what I was planning to discuss today, but let me conclude with one more point of view. On computation of K theory of projective space. So we've looked at K theory of projective space from left, from right, from top, from the bottom, from the front, and now we're going to have from behind. So this is so remember that kind of the basic axiom in equivalent cohomology says that if I want to compute, let's say, elliptic cohomology, G-equivalent elliptic cohomology of homogeneous space across some space X, that is the same as elliptic cohomology H, equivalent elliptic cohomology of the space X itself. So in K theory, that comes from the fact that, in fact, G equivalent coherent shifts on something like this is the same as H equivalent coherent shifts X. It's not just the K theories are the same, but in fact the categories are the same. And so now in particular, if I want to know, in particular, the projective space of dimension n, that is un plus 1 over un. Okay. Oh, sorry, un cross u1. So we can call this group G and call this group H. Right? Everybody agrees with that? And so then by this rule, we should get that elliptic cohomology of, let's say, Pn itself, that should be just the elliptic cohomology of H of a point. And that is what? So this is, so in general, we discussed this, H is a compact group or reductive group or whatever. So this is abstractly, this is our elliptic curve odd times over Z with co-characters of the maximal torus. And then we mod out by the Weil group of H. That is to say, we take the n e n plus 1 and we mod out by Sn, permuting all by one variable. So this is going to be E cross Sn of E. Okay. And this map, so this has the map. And the natural map of that down to Sn plus 1 of E that is just that's the map to elliptic homology of a point. Right? And so this says that, but it's good that we computed it like that, because what do we get? We get using this equality. Maybe I'll just highlight this equality in yellow. Yellow means that whenever, that means what? That means for any space X, since we can compute, we've computed not just the homology of projective space, we computed the homology of projective space for respect to any bundle, particularly the trivial bundle. So for any space X, we have that elliptic homology of H of any space X. That's a pullback. So there's a map to, so this is from this yellow square. We then conclude that this is L G of X going to L H of a point, L G of a point. And so this is the diagram as pullback. I'm not trained enough in category theory to, I don't know how to really denote, people denote it by things like this, and maybe I'll just write pullback. So this corner is a pullback of that. And that's, and you think, well, there's got to be, again, it's got to be obvious. But again, this is one of those things that you don't appreciate the fact is, how deep is the fact until you realize it's false. I mean, it's false in some slightly more generality. It's generally not true. So the computation we did were not in vain, not true for general G and H, not even in topological key theory. And what's in the counterexample is sort of, it's embarrassing. So this is, we take namely, if I take the KGL2 equivalent case here of the simplest projective space, and this GL2 we will treat as H. So because this is really corresponds to homomorphism. We'll take a homomorphism of groups. So this is not true. This is not equal to, if you want to take the automorphism, so automorphism occurring case here of P1, automorphisms of P1, this is PGL2, which we denote by G. And so if we extend the coefficients, that is not true. So there is a map. There's a map this way, but it's not subjective. No, sorry, the map the other way. I'm sorry. This map this way. No, this map is, there's a map the same. So if I have a G bundle and can make an H bundle out of it. So okay. So this is, here's map this way. And this is not surjective. Kind of really embarrassing. And the class which is not in the image of this map is just the O of 1. It's not in the image. So maybe a good homework to think about it. And there's, in general, if you ask for this kind of, this diagram to be a pullback, there's a very long discussion of which groups and which homomorphisms are okay. And this is we've proved it for, this is really pullback. So all we need is, okay. With current technology, we can prove it for what? Okay, for when G mod H is one of these forms. So it could be projective space or Grassmannian is also okay. By the same argument, the same way we did cohomology of projective space, we could have done cohomology of Grassmannian and see it okay directly. Or could be the additive group. So maybe I'll just write C, or C star could be okay, because both of these are of the form P1 minus 1 point or 2 points. And this is the same kind of reasoning we did as with the Tom space. We can one can do the same kind of reasoning and see that all the formulas go through like that. And so what you need is you need to be able to say that this object here, what would you like to say? So this surjectivity is equivalent to the statement is that whether this is, so what would you like to say? I'd like this object to be the same as I take kind of the, well, I'd like to take, I kind of like take this, it's like a Kunis formula for this product. So since I'm out of time, I don't want to impose on you further. But maybe we'll stop here, and I should maybe take some questions. So other questions about what I said, or about what I didn't say, or any other questions or any other kind. Yeah, so this is a homomorphism in general. If I'd like the so the homomorphism doesn't have to be the case that this you take. You can still kind of take the you can take the group, module the image of homomorphism. Is that what you're asking? So it's going to be this that map, instead of having a quotient, will have a kernel. So if you have a map between the groups, it might have a kernel, which is a normal subgroup in the first, and it might have like a quotient, which is homogeneous space in the second. That makes sense. So GL2 does map to GL2 maps to PGL with the kernel, which is of order 2, and that kernel that makes less complicated. Any more questions? Well, if not, I thank everybody for listening, and we continue next week.